Welcome to day 32. Today, we're diving into one of the most practical skills you'll need as a machine learning engineer, hyperparameter tuning.
So you've probably been here before. You build a model, your training metrics look amazing, maybe 99% accuracy, but then you test it on new data and the performance just tanks. This gap is a classic frustrating problem. What's going on? And more importantly, how do we fix it?
Well, in the next few minutes, we're going to break down exactly how to set your model's external control dials. This is the key to making sure your model works great, not just in the lab, but out in the real world where it actually matters. To really get the intuition here, I want you to think of your machine learning model like a high-performance engine. Now, this engine has two kinds of settings: the ones a mechanic adjusts before a race, and the internal parts that adjust themselves while the engine is running. And this difference is absolutely crucial. On one side, you've got hyperparameters. These are the external dials that we, the engineers, have to set before we even start training. They control how the model learns. On the other side, you have the parameters. These are the internal variables, like the weights in a neural network, that the model learns from the data during training. We don't touch those. Our job is to set the dials just right so the engine can learn effectively on its own. And that brings us to the formal definition. Hyperparameter tuning is really just an experimental process. It's all about finding the best combination of these external dials. And the goal is very specific. We want to maximize the model's performance on new, unseen data. It's less about finding a perfect formula and much more about disciplined experimentation. So when we're turning these dials, what are we actually trying to do? What's the goal? The answer lies in one of the most fundamental ideas in all of machine learning: the bias-variance trade-off. Here's how you can think about it. A model with high bias is too simple. We call this underfitting. It's like using a go-kart engine for a race car. It just doesn't have enough power to learn the important patterns, so it performs poorly everywhere. On the other hand, a model with high variance is too complex. This is overfitting. It's like an engine tuned so perfectly for one specific track that it fails on any other. It has basically just memorized the training data, including all its noise, instead of learning the real general signal. So hyperparameter tuning is really a balancing act. We're searching for that sweet spot, a model that's complex enough to capture the real patterns, but not so complex that it starts memorizing noise. The goal is to get both low bias and low variance. Okay, so now we know why we tune. Let's get into the how. How do you systematically find the best settings for these dials? Well, there are a few common strategies people use. The first and most basic method is grid search. You can think of this as the brute force approach. You just define a list of possible values for each dial, and it tests every single combination. It's thorough, for sure, but it can be incredibly slow. A more efficient way is random search. Instead of a fixed grid, you give it a range of values for each dial, and it just tries random combinations within that space. This actually works surprisingly well because it turns out that usually only a few of the dials are really doing the heavy lifting. And finally, there's Bayesian optimization. This is the intelligent approach. It runs a test, looks at the result, and uses that information to make a smarter guess about what to try next. It learns as it goes, so it doesn't waste as much time exploring bad combinations. So, which one should you pick? It's a classic trade-off. Grid search is fine for a small number of dials. Random search is a fantastic default for bigger problems because it's so much faster. And Bayesian optimization is the most efficient. It's perfect when each training run is really expensive, though it does take a bit more work to set up. All right, let's make this feel a bit more real. What do these dials actually look like for some of the models we use every day? For a neural network, one of the most important dials is the learning rate. This controls how big of a step the model takes as it learns. Too big, and it'll overshoot the best solution. Too small, and it might take forever to get there. For a model like XGBoost, you might tune something like max depth, which limits how complex each decision tree can get. And for a support vector machine, a common one is C, which controls the balance between making a clean decision boundary and getting every single training point right. And this is exactly why we care about tuning. Using a model's default settings can get you a decent result, but carefully tuning them is often what turns a simple proof of concept into a robust, high-performing model that you can actually use in production. So, to wrap it all up, hyperparameter tuning is simply the disciplined experiment of setting your model's configuration to get the best possible performance on new, real-world data. And that leaves us with a pretty important question to think about for our own work. How much performance are you leaving on the table just by using the default settings?